More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at home. Real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at home is right for your child, visit mathnasium.com/at-home. Mathnasium at home, changing lives through math.
Hello everyone, welcome back to the Mathnasium Schoolhouse. I am John, the AVP of Education and Training for Mathnasium. And today I want to talk about some cool things related to prime numbers and then touch on one of the great unsolved math problems in history, something called the Goldbach conjecture. And a conjecture simply means something that's assumed or believed to be true. So whenever in math somebody refers to something as a conjecture, you're just thinking that's something that just remains to be proven. So today, my goal is to just give you some really cool things to think about related to prime numbers. We're going to do a little activity. So if you have the worksheet that I put in Facebook, it'll be helpful. If not, you can print it later and you can rewatch the video and kind of go through the process a little bit. So today, kind of what you need to know to be able to follow along with the lesson, just kind of what a prime number is, and we'll do some exercises with counting and some basic addition. And if you can do all of those things, then we're good. Okay. So with all of that said, let's talk a little bit about prime numbers. So my first question to you is, what is a prime number? Then you can type your answer in the comments and introduce yourself. If you're at a Mathnasium center, of course, I'd like to know where you're from and where you're watching it from. If you're a parent, hopefully we'll go over some things that you can discuss with your kids later. And like I said, there'll be a couple activities that you can do as well. Okay. So a prime number is any number whose factors are 1 and itself. So prime number, the factors are 1 and itself. Okay. And so let's start thinking about the numbers that, kind of the numbers that we're comfortable with. So what about 0 and 1? Are 0 and 1 prime? Zero and 1, hopefully are not prime. Okay, so whenever we're thinking about prime numbers, and maybe some of them, we know that we don't include 0 and 1. They're not prime numbers. What about 2? Is 2 a prime number? And the answer is yes, 2 is a prime number. Think about the definition. The definition of a prime number is it has factors that are 1 in itself. The factors of 2 are 1 and 2. So by definition, it's prime. But what makes 2 special? So 2 is special because it's the only even prime number. And why would that be true? What do we know about even numbers? So like 4 or 6 or 8 or anything, any even number for that matter. We know that they're all divisible by 2. So if the definition of it being prime, a number being prime, is its only factors are 1 in itself, then, for example, 6 has a factor of 2. It's 2 times 3, right? So it doesn't fit our definition of a prime number. And we know that if it's not prime, then we call them composite, that they have factors other than 1 in itself. Okay, so 2 is special because it's the only even prime number. Okay? And some of the primes maybe you know, you can type them in the comments if you'd like, but 2, 3, 5, 7, and so on. And we'll dive into pulling out some of the prime numbers out of a list later on. So we know 2, 3, 5, 7 are prime, and other than 2, like I mentioned, 2 is the only even prime, which would mean that all the other prime numbers have to be odd. Okay? That doesn't mean that every odd number is prime. We know that's not true. We know 9, for example, is not prime, okay? Because it's 3 times 3. It has a factor of 3, okay? So odd numbers can be composite. My next question to you is, do you think there's a biggest prime number? So hopefully you know that there is no biggest number. Maybe that's something that you've talked about in school, or maybe with your parent or guardian or someone. There is no biggest number, right? The biggest number that I can think of, there's always another number that's larger than that. And that's also true of prime numbers. There is no largest prime. Okay? That means that whatever the largest prime number I can think of is, there is always a prime number that's bigger than that. Okay? And which is cool, is because there's an infinite number that are bigger than that too. And what's interesting about that is, so if you've been with me or seen some of my lessons, we've talked about Euclid in the past. And Euclid lived around 300 BC, which is a long time ago. It's about 2,300 years ago. And he actually proved that there are an infinite number of primes. So even going back that far, prime numbers were a topic to be studied. Euclid, and actually, if you want to look up something later, or if you're a parent and want to kind of look up some stuff with your kids, the Euclid's proof that there are an infinite number of primes is actually really elegant and simple. It's actually not that bad. You would think it'd be complex, and it's not. So it's kind of cool that it's been known for a long time, but it also goes to show you how important prime numbers have been in history. So there's a little bit of history and background on prime numbers. Another thing I wanted to kind of talk about is the concept of twin primes. Okay. So does anyone know what a twin prime is? So twin primes are kind of pairs of primes, and they're like, for example, 3 and 5, 5 and 7, 11 and 13. They're all considered to be twin primes. So they're kind of pairs, right? And there's no such thing as 3 consecutive prime numbers. And that makes sense because if I have 3 consecutive 3 numbers in a row, then at least one of them has to be even, which means it has to be composite. Okay, so you can think of these twin primes as being an odd number, an even number in between that doesn't count because it's composite, and then there's another odd prime number. So 3 and 5, 5 and 7, and 11 and 13 are examples of what we call twin primes, which is also something that's studied. So now the next natural question is, do you think there are an infinite number of twin primes? Do you think there's a biggest one? So if there are an infinite number of individual primes, do you think there are an infinite number of these pairs? And that interestingly has not ever been proven. There have been attempts at it, but It hasn't been proven, okay? Which is kind of interesting to think about, that something very closely related has been known for thousands of years, but this has not been proven. And it's strongly believed to be true, but not proven all the way, okay? The largest prime number that's been found has nearly 25 million digits, which is huge. What's even more interesting is that there's something bigger than that. It just hasn't been found yet. And there are ways to find prime numbers. And when computers are working to find the next prime number, it's because they've been programmed with ways and expressions to be able to find them. And they try to find the next biggest one. But it's interesting to think that no matter how big that number is, that there's always a bigger one to be found. And that's very much true. So even though we know there are an infinite number, that a bigger one does exist, you can't find them all, and there's a biggest one that's been found, and they need to find the next one. So those are just some interesting facts about prime numbers and things for you to know. So like I said, this is an example of a few prime numbers. We know the definition. And there are ways for you to find prime numbers. Like if I give you a list of numbers, you either can memorize them, or there are some ways that can help you find them. And that's what I want to talk about for a few minutes today. Okay. So here's another one of my math historical friends, Eratosthenes. And what's cool about him is he lived probably about 2,200 years ago. And what's interesting about him is he actually he's probably best known for being one of the first people, if not the first person, to calculate the circumference of the Earth. And think about how much that speaks to the power of what you all are capable of and what humans are capable of, that 2,200 years ago, he was able to calculate pretty accurately the circumference of the Earth with all the measurements that he had at hand, which is really cool. He was also, because he was so interested and so proficient at a lot of different things, his nickname was Beta, which was affectionate. It meant that he was believed to be the second best in the world at everything. And it speaks to why it's so important. Way back in history, people really cared about studying as many subjects as you possibly could, and being really great at a lot of different things. And that was very much true of him. And he gained notoriety for that. But what he also gave us was a method by which you could take and pull out primes, a sieve. Like, think when you go to the beach and you scoop out sand and you shake it. There's little rocks and things in that basket. And what I'm going to do is, in a very similar way, I'm going to take a list of numbers and I'm going to pull out the prime numbers. And that's where you're going to need a list of numbers from 1 to 100. And I gave you one in that worksheet. And if you want to just follow along, you can do it later and watch the video again. And it's a pretty simple process as long as your count bys are good. So here's a list of numbers from 1 to 100. It looks very similar to the one you have. And the way this works is it's kind of an algorithmic approach. It means I'm going to do something over and over and over again. I'm going to reach a stopping point, and then I'm going to go back to the beginning. And what I want to do is cross out 1, because my goal is to take this group of numbers and find all the primes. And we know 1 is not prime, so I'm going to cross it out. Now I'm going to circle 2. And we talked about how 2 is prime, so I'm going to circle 2 because it's a prime number. And I'm going to cross out every multiple of 2 in this list. Okay, so this is kind of easy because my first time through, I'm just going to cross out every even number because we know that all the even numbers are multiples of 2. So I'm going to cross out 4, 6, 8, 10, and so on. So take a moment and cross out all of the even numbers, all of the multiples of 2. And I'm crossing them out, remember, because they're not prime. And if you want to do it fast, you can cross out the entire row and kind of sketch it out if you want. But I'm going to cross out every one of these. And you can do the same. And what's cool about this is that it doesn't have to be just a list of numbers from 1 to 100. I can take a list of any size and do this process, and it will pull out all of the primes for me. Okay. Once I reach the end, I stop because I'm at the end. I go back to the beginning of the list and I circle the next number that's available, which in this case is 3. And we talked about a moment ago that 3 is prime. It makes sense that I'm going to circle 3 because it's prime. Now what I want to do from here is repeat the process, but you have to be careful because it's not quite so easy. I need to cross out all the multiples of 3. And some of them have already been crossed out because, like, for example, 6 is a multiple of 3. It's already been crossed out. I need to cross out any other multiple of 3 that hasn't been crossed out yet. So 9, 12 is already crossed out, 15, 18, 21, 24, 27. Count by 3s, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 72, 75, 78, 81, 84, 87, 90, 93, 96, 99. Okay. So I've crossed out all the multiples of 3 that haven't already been crossed out. I'm at the end of my list. I go back to the beginning. I circle 5. Now, it gets easier as you go on. I don't have to cross out nearly as many things. I want to cross out all the multiples of 5, but notice I've already crossed out many of them because all of these, 10, 20, 30, they're all multiples of 5. They've already been crossed out. So all I need to do is cross out anything that ends in a 5. So that was pretty easy. So I'm at the end. I go back to the beginning. I circle 7. And this one's a little bit tricky, and you have to just be careful. You're going to cross out all of your multiples of 7. And a lot of them have already been crossed out, and that's okay, but just take a moment and see what you get. And I'll cross them out and see if we end up in the same place. Okay? So whether you know your multiplication, 7's multiplication facts, and those in this kind of go beyond what you normally memorize because 91 is 13 times 7, so that kind of goes a little bit beyond, or you're really good with your comp bys. Either way, if you're careful, you'll be able to cross all of these out. Okay. So I've reached the end, and the question is, like, how do I know when to stop? Because if you went and circled 11 and started looking for your multiples of 11, they're already crossed out anyway. And the way this works is I stop, and this might be a little bit tricky for you. I stop whenever I reach the square root of the last number in my list. Okay? Now, this is a little bit tricky. Maybe you haven't learned this yet, but what's the square root of 100? It's 10. It's 10 because it's 10 times 10. So I don't have to go any further than 8 doesn't work, 9 doesn't work, 10. These are all composite. I reach 10 and I know I can stop. So what that means is if I had a list of numbers from 1 to 200, I would stop doing this cycle once I've reached the square root of 200, okay, whatever number that is on your list, okay? And so it'd be between 14 and 15. Now, what does this all mean? It means that once I've reached that stopping point, any number that hasn't been crossed out must be prime. These are all prime numbers. I just want to make sure I don't miss any. So it's something to practice, and it's something to show someone else, okay? Because it's a process that you can easily kind of show somebody what to do and work along with your child, or show somebody else how to do it, okay? Everything that's circled is prime, and that's a way to take any list of numbers and pull out the primes for you. And then once you've encountered them enough, then you memorize them, and then you don't need to do this. But like I said, it's just an interesting thing to know and something as an activity. Okay. So a couple of other real interesting prime-related things. And this, if you were with me on my session about the golden ratio, I kind of showed you Pascal's triangle. So if you weren't with me on that in that session, that's okay. You can look this up later. And it's not a surprise. Pascal's triangle there's so many connections to mathematics in this triangle, and it's not a surprise. There's a connection to prime numbers in this triangle as well. Okay. And this one is not so bad. This is an example of Pascal's triangle. You can create this yourself. Does anybody know, or you want to type in the comments, how do you create Pascal's triangle? So remember that each number is the sum of the two above it. So 1 plus 1 is 2, 1 plus 2 is 3, 5 plus 10 is 15, and you start at the top and you create the triangle using that as your pattern, and you can do it by hand. Okay. Now, I gave you an example because I wanted to point this out to you because it's a cool connection between Pascal's triangle and prime numbers. On this diagonal, I'm going to circle the prime numbers. And remember, Pascal's triangle goes on forever. You can find huge examples online. And the first few rows that have the prime numbers as its second value they're not very interesting. But I want you to look at this row in particular and these numbers. I mean, you can look at this one too. But what is true about 7 in all of those numbers? All of those numbers are evenly divisible by 7. What about these? Some of those are tricky because they go beyond your multiplication facts. But think about this one and think about what we just learned about this row here and see if you think that's true for all of those. Every one of those numbers in that row is evenly divisible by 11. Okay? And same thing with 13. All of these numbers that I'm underlining right now are all divisible by 13. So if I have Pascal's triangle, any of these rows that contain that prime number, all of the numbers in that row are divisible by that prime number, which is really cool. And something for you to practice building the triangle and practice your divisibility. Like how many times does 11 go into 165? It's something for you to practice. Very good. Now, I also mentioned something, let's not jump that far ahead. I also mentioned something called Goldbach's conjecture. Okay, now this happens to be one of the great unsolved math problems that there is. Okay, and it's while the greatest mathematical minds that have existed have tried to prove it, and there's some proofs out there that are not accepted, but they've tried. It's interesting because it's not a hard thing to understand what it is and what it is that you're trying to prove. Okay, and what it says is any even number greater than, so that's a greater than sign, remember, greater than 2 can be written as the sum of 2 prime numbers. So you look at that and you think, wow, it's not too bad to understand what that's saying, and we'll talk about an example in a moment. But it's the whether or not that's always true has baffled really brilliant mathematicians, and maybe one of you out there someday will prove it yourself. But let's take a look at an example, because what an example looks like of this is not too hard, and that's why I wanted to bring it up to you, is because it's a cool thing to think about, and it really is just kind of a basic addition thing. So what it says is so remember, any even number. So here's an even number 4. Okay. So any even number greater than 2, we know 4 is greater than 2, can be written as the sum of 2 prime numbers. That's all that says. And what that means is I can think of any even number greater than 2. It doesn't matter if it's 16 or it has 20 digits. It doesn't matter. I can write that number as the sum of 2 prime numbers. Okay? Which is interesting to think about. But it's also, it seems like something that, given all the really complex things that have been proven in math, that wouldn't be that hard to prove. But it is. And this conjecture came out around the late 1700s, so not nearly as long as the other prime number stuff that we were looking at earlier. Okay. So what this means is what I want to ask you is, how do you write 6 as the sum of 2 prime numbers? Like, we know 6 is 1 plus 5, but that doesn't work because 1's not prime. So how do you write 6 as the sum of 2 prime numbers? So 3 plus 3. Okay. What about 8? So remember, we're looking for 2 prime numbers, so 2 plus 6. Neither of these are both composite. But I can write 8 as 3 plus 5. Okay. 3 and 5 are both prime. What about 10? So remember, 10, even though it's equal to, let's say, 2 plus 8 or 8 plus 2, these are both, well, sorry, 2, I said in the previous one 2 is composite. It's not. 2 is prime, but 6 is composite. 2 is prime, 8 is composite. It doesn't work. That was my mistake. But 10 can be written as 3 plus 7. 3 and 7 are both prime. What about 12? Five and 7? So 5 and 7 are both prime. Okay. Now in your worksheet, I ask you, I give you bigger numbers to think about. And what's interesting, and it's even true with 10, is that sometimes there's more than one answer. Okay? And as a matter of fact, the larger the numbers get, the more options there are. Okay? So sometimes there's more than one possible answer. 3 and 7 are both prime, as are 5 in itself, right? So what about, let's say, 50? And if it helps, you can go back to your list. So how can you write 50 as the sum of two numbers from this list? And there are actually 4 different ways to do it. And if it helps, you can start with the smallest one you have, which is 2, okay? But that's 2 and 48, and we know 48 is composite. But 3 and 47 works. Okay. 45 is composite, so 5 and 45, that doesn't work. But 7 and 43, 7 plus 43 is 50. And I'll leave the other 2 for you to find, or for you to type it in the comments when you find it. Okay? And I also have on your worksheet, or if you want to practice it later, I also ask you about 100 and see how many pairs of primes you can find. And there will be a pair of numbers that add, a pair of prime numbers that add up to it. And this has been proven to be true through 400 trillion, I believe. So you can pick any even number up to 400 trillion, and you'll find a pair of primes that add up to it. I believe that's as far as it's gone. One last thing I want to show you, which is kind of a cool visual of this whole thing. And especially if you're a parent, or if you're a child and you want to ask your parent to give you, you may not be able to tell that that's actually grid paper underneath here. That helped me organize this. And I wrote all the numbers from 1 to 17 down either side. Okay, and then what I would want to do, and that helps me stay organized. And grid paper really helps with this because it helps you keep everything straight. And what I would want to do from here, after I've written those numbers diagonally, I would want to erase anything that's composite. And I want to do that on both sides. And like I said, the grids really help. So you can print grid paper if you have some at home. It really helps a lot here. And then what I want to do is I want to draw diagonal lines, and I do have one on the next slide so you don't have to watch me draw a bunch of diagonal lines. But I draw them in connecting corner to corner coming off of each of these numbers. And I want to draw them parallel to one another. So that's how the grids really help you. So use a ruler and connect corner to corner down the line. And I do it both ways. Okay. So I want to draw it that way. Okay. Now, like I said, I know you don't want to watch me draw that, so I've already drawn one for you. But what I'm interested in are these intersection points. Okay, so remember, we're talking about taking 2 prime numbers and adding them together to create any even number greater than 2. So look at this intersection, which represents 4, because it's 2 plus 2. Look at where these two cross here, which represents 6, 3 plus 3. Because remember, I'm only looking for even sums because the conjecture says that I can create any even integer greater than 2. So there's an intersection here for 5, but I'm not trying to make odd numbers. I'm trying to find even sums. Now, what's cool though about this entire visual is we know some of these have more than one option. Okay, so look at this one. And this is a cool way to explore visually the fact that there are often more than one combination of numbers that I can add together to get this. Okay. These both represent 10, but this one represents 5 plus 5, because that's where 5 and 5 cross. And this one represents 3 plus 7, because that's where 3 and 7 cross. So visually you can see, by looking at these intersection points, how many combinations you have. And it's a good project to work on with your kids, or if you're a kid, you want to do this yourself, carry out these prime numbers as far as you can on the paper you have, and you'll start to see where these cross, and that will tell you what the combinations are to make that number, which is a really cool visual that demonstrates that conjecture. And it shows you when you have multiple combinations. So with that, I'm going to close out this session of the Schoolhouse. I hope it gives you some interesting things to think about with prime numbers. I hope you practice finding your primes. I hope you practice creating this and finding all the combinations of primes that add up to all these even numbers. And I hope you think about all the cool possibilities and all the interesting mathematics out there. I will be back tomorrow. We'll be doing some more mental math. So if you've joined me for the mental math sessions, I'm looking forward to being back with you tomorrow at 11 a.m. Pacific to do that. Thank you for all your hard work, and I will see you all tomorrow. Bye now.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.